Welcome to Strive for Sustainability, Solid Waste and Recycling Virtual Technical Program. This is the last of the 6 sessions in the 3-day event. Hopefully you've all been with us for all the previous ones. My name is Rich Bills. I'll be the facilitator today, which means I'll basically introduce the moderator. And I'll go through a little bit of housekeeping as well. I'm the president of NYSSWAM. Also work for Steuben County. I'm going to go through, let's see if we can go to the next slide. The basic guidelines, you probably know these by now. You should be cameras off and muted if you're attendees. There is a Q&A button down at the bottom of your screen. If you have questions throughout the presentations, feel free to click that button and then type in your question for one of the presenters or the moderator. And Ken Armellino will be moderating today. He'll be able to distribute those questions around to the different people as necessary when he gets that right opportunity. The presentations are being recorded as well, so they can be viewed later. And I believe another question that seems to come up quite a bit is, will the presentations be available later? And I believe that if the presenters would like to make them available, they'll be available on the Federation website in the future. PDH certificates. So this is a PDH eligible situation here. At the end of the PDH eligible session, you will be emailed a form. Please complete it, sign it, and send back to Luann Meyer at the email address that's on the screen right now. If the records show that you are registered for the event, we'll send you the certificate of the completion within a couple weeks. You are required to be present for the entire presentation this afternoon to be eligible, so make sure you hang around until we're done. Next slide. Okay, so today we'll be talking about trash today, power tomorrow. I'll let Ken get into that. And I think we have one other slide to get into. And before I hand this over to Ken, just be aware that there are some conferences that are coming up that are part of the Federation. NYSAR is going to be having their annual recycling conference. Normally it's in Cooperstown. They're going to be doing a full-fledged virtual conference this year, which should be interesting. November 17th through the 19th. And then SWANA is doing the 2020 MRF Summit, basically at the same time, November 18th through the 19th. So be sure to check those things out. That's it for me right now. I'm going to pass this over to Ken Armellino, who will be your moderator for today's presentations. Ken, take it away.
Thank you. Thank you, Rich. Before we get started, I just do want to thank the Federation and its member organizations for putting this together. I've sat in on all the sessions so far. They've been very informative and very diverse. So they did a great job. Particularly, I know Luann and Russ Rakowski did quite a bit of work on it along with Rich. So thank you guys for your effort. As Rich mentioned, this is a PE session. So one of the aspects of that is we do need to go the full time to get the credit. But that does include questions and answers. So please, as you do have them, another reminder, put them in the Q&A box and we will address them. Each presentation is about 20 to 25 minutes. Probably take 1 or 2 questions if they're directly related to the presentation at the end of each one, and then move on from there. And at the end, if any more questions have come up, in general questions, we'll address those. So with that, I'd like to kick it off and welcome Dio Phagoo. He is, oops, I lost my notes. Dio Phagoo, he's a Senior Vice President at Anaergia. He's received his Master's in Chemical Engineering from the University of Toronto, and he's going to talk to us today about processing food and extracting it from municipal solid waste. So Dio, please take it away.
Thank you, Ken.
And let me just say, Dio's having an issue with his camera, so you will not see him, but you will see his presentation.
Yes, and let me know you can see that.
Yep.
All right, thanks, Ken, and I appreciate it. I'm sorry about the technical challenge. My camera decided not to work today, even though I put on a new shirt, so I don't know. And I appreciate that the opportunity to present at the Federation. I would have liked to do it in person, but I didn't know why. So I'm going to talk today about food waste extraction from mixed solid waste at and North America's largest facility. Before I get into that, I will talk briefly on just maybe a couple of slides here on Anaergia, and our vision is really taking different kinds of waste and mainly focusing on organic waste from wastewater or solid waste, food processing or agriculture, and using an integrated solution, proprietary technologies with solutions to provide renewable energy, renewable gas, recyclables, fertilizer, and clean water. So that's sort of the overall our overall vision. We're a Canadian company with main office in the US as well, in Carlsbad, California, and offices around the world in Europe, Asia, and Africa. And a vertically integrated companies where we develop technologies, but we also present solution and even own assets. Some facilities across the globe includes some mixed waste processing facilities in South Africa, Cyprus, India, and some source separated organic processing facility, for instance, in Toronto and in the UK, just as an example of some of the different mixed waste and solid waste facilities that where we target organics. Getting closer to home, some of the facilities that we are either operating or in construction. It is in San Carlos in California. This is and in Sun Valley, California. These are the organic extrusion press at a transfer station for separating organics from commercial solid waste or mixed waste. And in Toronto, it's from a municipal facility for separating organics from source separated organics, removing the contamination and getting the digestible organics. And then along the bottom, you'll see some of the facilities where the extracted organics from solid waste will go to, like in Rialto or Victorville or East Valley. These are a digestion facility, anaerobic digestion facility, either merchant digestion facility or digestion facility at a wastewater treatment plant. Just want to kind of zoom in now into California itself, and here, the largest source of methane emission in California is from landfill, which accounts for about 41% of methane from point source emission in California. And you see, all the sort of the purplish color circles where landfills are emitting methane. And this sort of trigger the kind of California regulation SB 1383 for the diversion of organics from landfill. And this regulation really stipulates that they want to achieve a 75% organic diversion by 2025, based on a 2014 level. What this means that by 2025 going forward, looking at the projection and the organics that are generated, will require something like 20 million tons of organics to be reduced. And that's a phenomenal amount of organics that needs to be diverted. And the acceptable options for diversion of that organics are anaerobic digestion and composting. Those are the two acceptable methods. And you have to achieve, to do that, we're estimating, or there are some others that have estimated that it would require upwards of 200 organic processing facility in the state of California alone. Yes, California is population-wise is bigger than New York, but if something like this is to be mandated in New York, it will require a phenomenal amount of infrastructure. In addition, the organics that have to be applied have to meet very stringent composting standard or land application standard, meaning that things like rigid plastics, metal, glass, that's greater than 4 millimeter, which is about 1/8 of an inch or so, will need to be less than 0.5%. And thin plastic needs to be less than 0.1%. So it requires a diversion, but you're not looking at getting a dirty compost or a dirty organics that then you can land apply. It needs to be absolutely clean. Now, what we've seen to achieve one of the way of achieving this, one of the fastest way of achieving this is to extract organics in using anaerobic digestion technology to produce methane gas, capturing that methane gas and producing power or renewable natural gas. If you look at the carbon intensity or the carbon associated with landfill, it has a huge positive amount of CO2 per ton of waste. It's over 200 positive. Even composting has a small positive impact, even though it's significantly less than from a landfill. However, when you look at organics from separated and go to a wastewater treatment plant for co-digestion or dedicated digestion, you end up with a very negative impact. So it's a carbon negative fuel. You're generating a carbon negative fuel if you take organics to a anaerobic digestion facility, and specifically if you take it to an anaerobic digestion facility at a wastewater treatment plant. This is trigger sort of one of our approaches to organic diversion across the country, in fact. And this is not just Anaergia, but there are other entities that are doing this or looking at doing this as well, where we try to use existing infrastructure, especially associated with wastewater treatment plant, which has digester, which may have extra capacity or the ability to increase the capacity of those digester. And in addition to digesting wastewater biosolids, you're digesting, taking the solid waste, extracting the organics from it, and sending that to a wastewater treatment plant for co-digestion at the wastewater treatment plant. And this will generate significant benefit for the wastewater treatment plant in terms of tip fees and more renewable energy generation, but also results in a significantly negative carbon intensity. Now, before you get there, the question is how to separate the organics. There are two, philosophy around this, two approaches around organic separation. One is, separating the organic at the source, which is, separate collection where you have multiple bins, source separated organics, and then you're taking that to a compost or to a digestion facility. I could tell you that, source separated organics may sound great. And it's usually, for the first 5-10% of participation, it's relatively clean. But as you get up in participation to 50 or 60% of residents, you have an increasing level of contamination, and that in Toronto, for instance, we're, processing SSO with, 25-30% contamination. So it still requires a significant amount of processing. The other approach is to use, a mixed waste collection instead of separate collection, and processing that using mechanically separated, like a mechanical biological treatment process to separate the organics from the waste, and sending that organics to a digestion facility. Either it could be a dedicated digestion facility, or it could be a digestion facility at a wastewater treatment plant. Some of the benefits, I would say, for the mixed waste collection and sending it to a wastewater treatment plant is, with mixed waste collection, you're not trying to change behavior, in terms of separation and having separate bins and things like that. And it also requires in lower costs. You can also use existing infrastructure to process that organic. In addition, with separate collection, you have to look at the carbon footprint associated with separate collection of that organics as well. And that becomes especially important if you start only collecting a very small fraction of the organics that's in the municipality or in the community. If you're only collecting a small amount and expending a lot of energy in terms of both costs and energy in terms of collection, then you're defeating the purpose. And this sort of triggers, why we our preference is sort of the mixed waste process at, high diversion organic processing facility, where, everything or virtually everything goes into the same bin or bag, and then it gets processed at a high diversion processing facility, where you remove the recyclables, and you may be able to even generate some RDF if you can get an offtake agreement. But definitely you can generate the remove recyclables, remove the organics, that then goes to a digester, and then the non-combustible, non-digestible, non-recyclable material will then go to landfill. So there's still a place for landfill, but you preferentially would take recyclables out, organics out, combustible out, and then you send the rest to landfill. We've done some analysis on this and look at, both the sort of the collection of the organics as well as the processing and then transportation and disposal. And if you look, even if the numbers are not exactly the same, what it tells you with source separated organic collection, it results overall in a significantly higher cost when you get up into scale, if you're trying to achieve a high level of diversion, compared to a mixed waste collection and processing. With that said, I will sort of go through a case study based on a facility that Anaergia has designed and built in California over the last several years, and that's just coming online now. And this is the facility in Rialto, California. It's referred to as the Rialto Bioenergy facility for recycling of organics. Has a processing capacity of 700 tons per day of food waste. And this is food waste already extracted from commercial solid waste, mixed solid waste, as well as the ability to process over up to 300 tons a day of sewage sludge cake, dewatered sewage sludge from wastewater treatment plant. So this is a project that Anaergia developed, designed, finance, and will operate as well. For ease here, this project is really taking material from area solid waste, where organics will be separated at the transfer station one of the main facilities associated with this is a waste management transfer station in Sun Valley, California, which installed an RX press to separate the organics from solid waste and sending that organic fraction to Rialto, which is near San Bernardino. As well, the facility will take wastewater sludge from the surrounding area, including around the Rialto area, and process that biosolids as well. And I'll show you how. So, one may look and say that you need to process, everything at the same location. And that's not necessarily the case. You could process your solid waste in one location and process the organics in a different location. Similarly, if you could process the mixed waste in one location and you could separate it into a combustible material, a combustible residue that can go to a energy from waste facility, the organics can go to an anaerobic digestion facility, the recyclables can go to a MRF, and then your non-combustible, non-recyclable, non-organic digestible material will then go to a landfill. And that reduces, significantly the amount of material going to landfill, extend their life. It will also improve the combustion in the waste energy from waste facility, because you don't have all these metals and maybe plastics and chlorinated plastics and things like that. So you're sort of getting the best of all the different fraction of the waste stream. And then in the digestion, in the case of organics, will then go and produce biogas that then you have multiple uses for that biogas. And the digestate that comes out of that, the organic fraction, as well, you can convert that into, fertilizer project and have nutrient recovery for that fraction. In here, I'm just showing a quick example of different fraction of, source separated organics that's fairly contaminated, commercial waste and mixed waste that can then process, and this is just a schematic showing, will then process, maybe at a transfer station using, screens and the RX press, etc., to separate the organics, and sending that for an unpolished organic fraction will then come out. Will still have 2 to 3% contamination in it with, small pieces of thin plastic, hard plastics, glass, grit, etc. And then this go through a polishing step, to create a very, very clean organic fraction that then goes to a digester facility. So specifically on the Rialto facility here, we have a transfer station where the RX press is installed, operated by, in this case, waste management, that separates the organics from mixed waste, MSW, or commercial organic or commercial solid waste, and then sending that separated organics as a cake to the Rialto facility, which goes to organic polishing, followed by anaerobic digestion, and then the processing of the gas and the digestate. Similarly, the biosolids from wastewater treatment plant, dewatered biosolids, will then be brought into this facility. But because these are already digested biosolids, we're putting in here a drying facility followed by pyrolysis to produce a biochar, which is a higher value fertilizer. So there's a two-step process and then there's a significant amount of recovery of energy from the pyrolysis process to the pyro oil goes back into the digester, and the pyro gas being used, recovering the thermal energy in the drying process. And basically the pyrolysis is an energy positive process where you generate more energy than it consumes. So on the organic side, we separate the organics from the solid waste, sending that organic fraction for polishing, as I mentioned, 2-stage polishing, a dynamic cyclone to remove small pieces of plastics and floatables, etc., and then a hydrocyclone to remove grit, glass, stones, to produce a clean organic slurry that then goes to the digester. This is what the RX press look like in Sun Valley, and this is another one that's in Europe that shows a better view where the solids are entered into this hopper, and then it's fed into these revolver type perforated chamber, and it is subject to very high pressure to generate an organic fraction and a dry residue fraction. This is what the organic fraction look like. This is basically the first load of organic fraction that was delivered to the Rialto facility just a few weeks ago. And as you can see, it's a cake and then you can see there's still contamination in there that then gets into a live bin hopper that then gets fed to a polishing system. So this unpolished organics fraction then gets fed to a polishing system to produce this clean organic slurry that gets fed into the digester. This is what the polishing system look like. It has a dynamic cyclone for removing the small pieces of plastics and floatables that would be in the digester if you put the unpolished organics into the digester. And then from this dynamic cyclone, it goes into a hydrocyclone, double pass hydrocyclone to remove the glass, grit, sand, etc. And the clean organic fraction is then sent to the digester, and the grit is washed and classified and sent off-site. This is what the facility look like. This is the digesters that the organics will then, this is here. This is the reception area here. And then from the reception area, it gets fed into the polishing system. And then from the polishing system to some buffer tank, and then to the digester. And then these are the dryers, centrifuges, CHP, etc. So this is what the facility looked like from a rendering back in 2018. What we anticipate the facility will look like at the start of design. Sorry, I guess I can't see the comment, but I figure I have only a couple of minutes more. So I will just wrap up here. This is what the facility looked like today, as of this week. Sorry. So you see there's a receiving bin for the organics, the polishing system, storage tank, digesters, the biogas cleaning and then upgrading systems are here. There's a waste scale, then dewatering, drying. The pyrolysis system is not in place yet, but this is where it will go. CHP and wastewater treatment for recycling of the water back to the front end for dilution. And so this is a 5.7 acre site that's processing 1,000 ton a day, or will be processing 1,000 ton a day of organics from food waste and biosolids. So it's an extremely tight site. This is another view of what the facility looked like. Again, these are the reception for the food waste. The polishing system is here, followed by the buffer tank, and then the digester. The gas cleaning is here, wastewater treatment behind here. And with that, I would like to thank you. And again, I apologize that I could not share my video. I will stop sharing now. Oops, where is that?
Thank you, Dio.
Sharing and over back to Ken.
Thank you, Dio. One question we had that came in, for the MSWK, the processed material, And for the wastewater treatment plant component, is the material tested for PFAS prior to delivery to the facility or after processing?
The biosolids facility the biosolids cake has been tested for PFAS, and the digestion process is not going to remove that. But we've found excellent results right now with the pyrolysis process, and that drying and pyrolysis, the PFAS is virtually undetectable after the pyrolysis, high temperature pyrolysis, that will be installed next year on the biosolids train. But specifically for the food waste component from the MSW, we haven't done that. That's a good question, and I think we probably should do some testing on that as well for a long-term disposal.
Right. And then one last question before we move on. Someone asked, how much energy will the facility generate?
The facility will generate, it's about up to 1 million MMBTU of RNG per year. It's probably equivalent about 15 megawatt or so of electricity equivalent. We have the option of either generating RNG up to 1 million MMBTU per year, and to generate about 4.6 megawatt of electricity, but using CHP as well.
Okay. Well, thank you again, Dio. We appreciate it, and maybe we'll have some more questions at the end.
Okay. Thank you, Ken.
Next up, speaking on current ash reuse initiatives is Rebecca Guardino. And, if you're like me, if you've been come to this conference for a while, or if you've been in the waste or especially waste to energy industry like I have been for 31 years, ash reuse is something that's been talked about a lot. But certainly if you saw Rebecca's presentation last year at the Federation conference, and this year with the progress that's been made, I mean, it's almost, you could say that more progress has been made in the last 2 years than the last 30. So with that, Rebecca is a construction material engineer for Covanta in Morristown, New Jersey. She's received her BS in geology from James Madison University and her MS in geology from Rutgers University. So with that, I'd like to welcome Rebecca. Thank you.
Thanks, Ken. Good afternoon, everyone. I am happy to return to give a progress update on a lot of the different ash reuse initiatives that we've been taking on here at Covanta. It's a very exciting time for us. I'm a member of the Covanta Metals Management Group, and our major focus is to take a look at the ash residue that's coming from our energy from waste facilities and determining ways to extract more value and also to reduce ash disposal at landfills. So I'm going to kind of give you an update today from the presentation that I gave in May of 2019. So some of this might be a little bit of a review for those of you who were present, but we've, as Ken has mentioned, made tremendous progress over the last year, and I'm really happy to be able to show some samples today over video and talk about all of our progress. I'm sure many of you are familiar with Covanta. We're one of the largest owner-operators of infrastructure for conversion of waste to energy. We own or operate 45 facilities across North America and Europe. We convert 20 million tons of waste annually into over 9 million megawatt hours of electricity. We reduce 21 million tons of greenhouse gas annually, and we continuously power 1 million homes, and we recycle over 600,000 tons per year of metal. So Covanta's overall mission is to provide sustainable waste and energy solutions to ensure that no waste is ever wasted. But today I'm going to give you a brief introduction on the Covanta Metals Management Group, kind of review our areas of focus and the timeline of our accomplishments, talk a little bit about the vertical integration of our non-ferrous metal recovery, but really want to focus on our total ash processing system, or we refer to it as TAPS internally here. And we've made significant progress and a really exciting project, so I'm happy to be able to report on that with you guys today. But CMM Group has several major areas of responsibility. We've got business management and development, so we've got projects at our energy from waste facilities to either install or optimize our metal recovery systems at the energy from waste plants themselves. But we also have mobile assets, and we'll discuss that a little bit here this afternoon. The total ash processing system, or our TAPS system, development and deployment has really been a huge undertaking over the last probably 3 years, and we've reached that point where we're making product, we're producing, we're processing ash, and getting really positive results. Out of this whole total ash processing system, not only are we getting metal out of the ash, but we're also generating a usable aggregate product that can go into the construction market. So I'll give you an update on that today. I'll let you know where we're at. But then we still have, a little bit of waste from the system. So how do we realize the value from that and determine reuse opportunities? I had mentioned earlier, so we are generating upwards of 600,000 tons of metal per year. That's across the fleet. We do have folks whose entire focus is really getting those commodities to market so that we can recycle those metal. We have a new group formed whose sole focus is offtake agreements for these aggregate products. And we are embarking on a strategic plan for how to tackle this same issue in Europe for IBA processing and or fly ash disposal options. Continuous improvement and optimization is always a focus for us. So we're always looking at systems that we have in place. How do we optimize them? How do we make them better? Our fleet-wide goal for 2020 is to reach a 2% non-ferrous metal recovery. And as I show you kind of the different parts of our fleet here, you'll kind of see how we're able to achieve that. And again, on project execution and engineering, we have regional operations, we have retrofits going on at our energy from waste plants, and then again, that total ash processing facility that we'll discuss today is playing a big role. But since 2012, Covanta has invested in over 70 individual metal enhancement projects, and this is across the fleet throughout different areas of focus. One would be on the ferrous metal side. So we've been doing ferrous drum installations and upgrades at our energy from waste facilities. We've installed shredder and air classification systems, and we constructed and operate a regional ferrous processing facility, a non-shred facility, and we'll talk a little bit more in detail about that today. On the non-ferrous side, this has been a huge success for us. It's installing and optimizing non-ferrous separation systems, eddy current separators, where we focus on both the plus 10 millimeter fraction and also the minus 10 millimeter fraction sizes. What we're finding is the more valuable metal is in the smaller ash fractions. So how do we recover that metal where we can recycle it back to market? We've done a lot of tests on separating bottom ash from fly ash so we can get better metal recovery from that. And we also installed and operate now a central non-ferrous processing facility, and we'll talk about that and the success story there. On the mobile side, we realize it's not feasible necessarily to send everything to one centralized facility. And some energy from waste plants, it might not be feasible to do the level of metal recovery and processing that we'd like to do. So we have deployed mobile ash processing systems that will travel to an energy from waste site or a landfill site to mine and or process ash to recover the metal from it. And then the processed ash can be used at the landfill for construction purposes or just go back into that landfill for disposal once it's metal free, thus creating extra airspace for the landfill. And again, TAPS, total ash processing, that uses density separation to get even the smaller fractions of metal, and we'll kind of talk about that today. But when we look at conventional metal recovery technology, about 4 millimeters is about the smallest particle that we're able to recover with conventional technology. The real success story, and we'll talk about TAPS today, is that we're now getting to the micron size. So in the past, about 4 millimeter was the smallest we could recover. Now we're getting down to the micron size metal with our TAPS technology. So huge success for us, and we're really excited. So the Covanta Metals Management Group really formed in 2012. It started with 3 people, and now we're at, I believe, over 30. And the areas of focus for our group have kind of evolved as we've learned more about our product. So 2012 and 2013, we were really focused on how do we get the metal out at the energy from waste plants? How do we effectively recover that ferrous and non-ferrous metal? But as we were becoming more and more successful at metal recovery, we started to take a look at the ash itself. So 2014 was a huge research initiative to look at ash. What's in our ash? What value is still left in there? And how can we reuse these materials? So in 2015, we built a pilot plant processing facility at a third-party research lab, and we processed ash from various energy from waste facilities across our fleet through a wet processing technology, through a density separation technology. We're able to validate that we can recover these small, very micron level size particles of metal, but that the inert material that's left is actually a really good construction material. It looks like aggregate, like a sand or a stone that you would be finding in a construction market today in applications like a hot mix asphalt and ready mix concrete. So while we started kind of learning all of this about the pilot plant, at the same time we started looking at our central processing facilities, understanding that at the energy from waste plants, we were very successful at recovering both ferrous and non-ferrous metal, but that these metals were still had some ash on them. It was a varying size, and we really weren't able to see the real value from them. So in 2016 and 2017, we built our centralized ferrous and non-ferrous facilities where we will take that metal from our energy from waste plants, do further processing, further cleaning, further sorting, and realize a lot more value to that metal. 2018 was really the kickoff to our TAPS, our total ash processing system, by us picking our site and applying for a permit from the Pennsylvania DEP to allow us to process energy from waste ash to generate a construction material. We kind of giggle amongst ourselves internally. We're kind of modern day prospectors in what we're doing. So we've talked about kind of the evolution of the different stages and the different roles of CMM over the years, but since we really started looking at metal and ash in 2012 to where we're at in 2019, it's been a significant increase in both the ferrous and the non-ferrous recovery that we're able to do annually. 2019, we ended the year with over 570,000 tons of ferrous metal recovered and over 56,000 tons of non-ferrous metal recovered, far exceeding our initial expectations, and we're seeing that these numbers are just continuing to climb. So as far as metal recovery, we're actually over 600,000 tons now of metal each year, and that's really enough steel to build over 400,000 automobiles and enough aluminum to manufacture more than 3 billion beverage cans. So we're talking about a tremendous amount of metal that we're able to return to the market that otherwise would be going to landfill. When you look at our environmental impact, so let's say we were not recovering all of this metal to produce and mine this new steel, aluminum, and copper. It's a really carbon-intensive process. So if this metal was going to landfill, it would be lost forever. But we're able to save more than 1.2 million tons of greenhouse gases every year. And that's the equivalent of taking 113,000 cars off the road every year. So it's truly significant the impact of our metal recovery has been. So we briefly mentioned our ferrous processing facility. We kicked that off in 2015. We're able to kind of get the remaining ash off that metal, separate it into different sizes, and sell it to third parties. It's a higher quality because we've done this additional processing, and we've been able to realize more value there. We can now sell both domestically and overseas, and we can even bale material for local processors. It's a nice facility. We're able to do a lot of processing there. The non-ferrous is really where we've seen our significant advancements. So instead of having a mixed non-ferrous metal, which would be lights and heavies combined, really with still some ash on that, our centralized non-ferrous facility separates this material by size, it separates this material by density, it cleans it, we're polishing it, and we're able to really realize the value of the different metal commodities that are in here. So instead of selling a mixed non-ferrous metal out to the market, we can give them a clean copper product or clean brass, clean zinc, a clean aluminum. And shockingly, what people love when they come to a tour of the facility, the highlight is always the coins. Think about how many times you vacuum out your couch cushions or your car, and you're sucking up all of these coins. Our non-ferrous processing facility is actually able to recover these coins, and just the volume of coins that are in the trash is just tremendous. So the non-ferrous processing facility, operating since 2017, has been a huge win for the Covanta Metals Management Group and for Covanta overall. But total ash processing, kind of why we're really here today to talk about it. Again, I had mentioned kind of in 2014, we started looking at the ash to say, what's in this stuff? Is this usable? They started to evaluate the ash, both from a chemical and a geotechnical perspective, and realized this stuff could be used in construction applications. There's definite benefit here. Early on, there was some progress made in Pasco County, Florida, where this material, bottom ash material, was used as a road base. So this TAPS process, this research initiative said, hey, this material's got some potential, and putting it into landfill, it really shouldn't be the fit. It's not the end of the story. We know that there was more metal, right? We were only able to recover, about 4 millimeter sized fractions. We know that this little bits of metal were still in the ash. How do we get this out? So we built that pilot plant that I had mentioned, and we successfully demonstrated that the wet technology works. We can get below 4 millimeter fractions of metal out of the ash, and it becomes a usable aggregate product on the output. So from that facility, we were able to learn that all products that we made, as well as all waste streams off of that pilot project, were classified as non-hazardous. They passed all the TCLP leaching tests. And it showed us that there's a potential to move these aggregates to market. So the next step was, let's build a plant. So that's what we did. Kind of the overall flow of TAPS, what is it? So we're taking ash from our energy from waste facilities. We're taking any ash that's liberated from our central ferrous and our central non-ferrous facilities, and we're putting it into our total ash processing system. This system is basically washing and screening circuits where we're able to separate the remaining ash by size and also by density. We have high intensity magnets to recover any ferrous material that might be remaining in the ash. And we have eddy current separators that are able to recover any of the non-ferrous that's left in that particular ash stream. We have specialty equipment to remove any organics, fibers, really lightweight floaty type material. And we have an extensive water treatment facility plant attached to this TAPS. We are a zero water discharge facility. And because we operate through a wet processing system, there was no air permit required for this particular facility. So our facility is located in Fairless Hills, Pennsylvania. So we approached Pennsylvania DEP with this concept, and they issued a general permit in March of 2018 for all of Pennsylvania that basically allows for the processing of ash residue to recover metal and or aggregate for use as a construction material. So a lot of work and attention went into working with the DEP to make that happen. That was really kind of starting in 2015. So it took about 3 years to get that permit issued. We submitted our permit application that June, and we heard back from DEP in December of 2018 that says, go ahead and build it. So it's been a kind of a long process to get the facility built. Obviously, no one ever really wants to build and start a brand new facility amidst a global pandemic, but we've been successful in doing so. And we're in startup and commissioning mode of the facility right now. So what are we actually generating? I kind of showed the little fractions of metal. We are recovering these fine fractions, less than 4 millimeter sized particles of metal out of the ash. But now what we're also generating is a usable construction aggregate. I know it's probably hard to see, the pictures don't kind of do it justice, but this is beautiful material. I come from a background of quality control in mining operations and quarries. I've worked for asphalt and concrete companies, so I'm very well versed on what that construction market is looking for from an aggregate, and we're able to achieve that with this total ash processing system. So you might kind of wonder, well, what the heck are we testing this aggregate for? We have an on-site laboratory at our Fairless Hills facility. We're testing metal in that laboratory, but we're also evaluating the aggregate materials that TAPS is generating. we're looking at a couple different parameters of that aggregate. One would be the gradation or the particle size of that particular material. Depending on whether it's going in asphalt or concrete, there are different specifications for the size of that aggregate to be usable. We're looking at the bulk specific gravity of the material, or the ratio of that mass per unit volume. So water has a specific gravity of 1.0. How heavy is your aggregate compared to water? The absorption of the aggregate is also a factor. So there is pore and void space within an aggregate particle. So moisture will be absorbed into some of that pore and void space. So how much water does that particular aggregate absorb? That's important when you're doing volumetric mix designs in both concrete and asphalt, and also the density of the material. We're talking about material in pounds per cubic foot. Are we looking at conventional weight aggregate, lightweight aggregate, heavyweight aggregate, that kind of thing? And all the analysis that we've done has been according to ASTM test standards. So it's a construction materials testing national standard that's used for all different construction applications. So, the first kind of step was taking a look at this aggregate and saying, what's the quality of the material that we're able to recover by looking at those various parameters we just discussed. Now, let's get this aggregate into a finished product. So we partnered with a university here in New Jersey, and we successfully designed some super pave asphalt mixes, incorporating the aggregate from the TAPS process into that asphalt. And I know it's hard to see and it's hard to appreciate how beautiful this is, but this is a sample of the asphalt that we've made with our university partner. We were able to meet pretty much all the DOT requirements. So when you're making asphalt, there's a bunch of different parameters that you need to test it for to make sure that it'll be a long-lasting pavement. And we were able to check the boxes on all of those requirements for the mix. We also have done some performance testing. There's only a few research laboratories in the nation that are able to do this performance testing. We were lucky enough that this was one of our partners. They had the ability to do some long-term moisture susceptibility, cracking, rutting potential tests on our asphalt that incorporated Covanta aggregate, and we passed those specs. So very exciting for us. We're like, this is great, this is awesome. We made it work in a lab, but does it apply to real life? Kind of glad the timing worked out really well, because last week we paved over 200 tons of 12.5 millimeter super pave asphalt surface course at our Fairless facility, one of the access roads, that incorporates our aggregate. So it's really our first successful test run. And you can see there's a picture here of the paving crew on our site laying down that asphalt. It looked amazing. We got great feedback from the paving crew, from the plant production facility. No one really noticed. I mean, it was business as usual. The aggregate really performed very well. And now we have this access road that we can study. We'll be taking some cores of the material, and we'll be studying that as well. What I neglected to mention, and I'll step back a second, is that with the aggregate that we are testing, I talked about a lot of the geotechnical physical parameters that were required to analyze. But there's also a whole host of environmental parameters that the DEP is requiring us to test for. So we have 21 inorganic and 41 organic constituents that we have to test the aggregate for both totals and leachable concentrations in order to reuse this material. So those are all conditions of the general permit. And we've successfully been able to meet those requirements. So really exciting. This road is a huge step for Covanta. We're very excited to kind of reach that milestone after years of studying. But asphalt really isn't the only market we're looking at. There's a couple other construction markets that we're looking at. Ready-mix concrete would be one of them. So we're taking a look at low-strength, non-structural applications. We don't want to put this in high-rise buildings, but things like slabs or footers or curbs. There's definitely a potential to use our aggregate in concrete mixes. Here's a cylinder that was produced at a local university partner, which has a percentage of Covanta aggregate in this concrete mix. We were successfully able to develop mix designs that incorporate our aggregate that hit between 3,000 and 4,000 PSI 28 days. So that's pretty much the bread and butter for the concrete market. That's their everyday mix. It's used in common commercial applications. And we've been bringing our aggregate to local producers, showing it to them, showing them some of this data, and there's really positive feedback. There's some excitement in the market to use this recovered aggregate. So very excited about that. And in addition to the aggregate, we're also pulling out or extracting a low-grade ferrous material from our tap system. And what we have found is that it could be a good fit as a raw material in the production of Portland cement. So Portland cement mix designs incorporate a small percentage of iron oxide, and our low-grade ferrous meets that criteria. So we have done 2 full-scale tests now, one in Pennsylvania and one in Florida, using our low-grade ferrous as a constituent in Portland cement. And the feedback's been very, very positive from those suppliers. So we're feeling very confident now that we've been able to kind of take a laboratory, look at things and now replicate it in the real world, and it's very successful. So, overall, there's been a huge evolution in our CMM group. We really kind of just started at looking at metal, right? We went to our energy from waste plants and said, how do we pull this out of the ash? And the great part about being in our group is that once we kind of check that box, we're moving on to the next iteration. We're constantly evolving. So the construction and operation of our central ferrous and non-ferrous processing facilities has been a huge benchmark for us. The mobile ash units that we have that are able to go on-site to landfills to recover metal has been a tremendous addition to the fleet. And now that we're at this total ash processing step, we're really excited for what the future holds for ash reuse. We kind of took it as something years ago. I don't think we ever would have anticipated that we would get, metal fractions as small as we're able to recover from this tap system. And definitely, I had a big smile on my face last week standing on the paving site, watching that asphalt go down with our aggregate in it was truly tremendous. So a lot of good things are happening here at Covanta, especially in the metals management group. I think when I was presenting last May, it was kind of like, well, we're going to build taps. We're hoping that the aggregate's awesome and that it's workable in a construction application. And I'm just really happy to be able to come today and tell you we're making it happen. And we're excited about what that brings for us for the future. So I appreciate everyone's time today. I'd be happy to take some questions if there are some.
Rebecca, welcome. Thank you very much. It's a great presentation. One question, which she may have partially answered, but has the material gone into the market, or when is it expected to go into the general or open market?
So right now we are in talks with several different end users. We have a couple different applications, end users that are interested in purchasing the material. We do have a PO actually for the purchase of material. So we're expecting before the end of this year to have material moving to the outside market.
Great. And this is something which I think may you may find some interest in. You mentioned the slide you showed that the first recovery, how it increased 35%. What you didn't mention, which I think is important to note on that, is our throughput only changed very slightly over that 5 or 7 year period. So
that's correct.
That was not because there was a lot more ash.
No, it's, our ash kind of has been relatively consistent. So, this increase that you're seeing is truly the benefit of all of these enhancement projects that our group's been focused on.
Okay. All right. Well, thank you very much, Rebecca. If any more questions come in at the end, we'll certainly get those on, but thank you very much.
Great. Thanks so much.
With that, I'd like to bring in our last presenter, Dr. John Atkinson. He's an associate professor at the University of Buffalo. He has a PhD in environmental engineering and civil engineering and has been in 36 publications. He's going to present to us on the greenhouse gas emissions associated with waste energy disposal of MSW. John, go ahead.
Well, thank you very much, Ken. Very excited to be here on behalf of my co-authors, Dr. Mohsen, Ghafari, and Dr. Michael Shelly. Michael is an environmental economist. Mohsen at the time was my PhD student, and he sort of led a lot of the quantitative work that you're going to see in this presentation. He's since moved on to bigger and better things and has a real job now. He's no longer a grad student. I'm also presenting, I think on behalf of the larger waste management team that we have at the University of Buffalo. I hope that one of the takeaways of this presentation is an idea about how academics can contribute to the broad waste management issues that we're dealing with in New York State and beyond. We have a very, very large plastics recycling team that is working directly with DEC. We just received a new $2 million NSF grant looking at sorting, sensors, valorization of waste plastic, things like that. We're working with multi-layer films and beyond. So this presentation should give you an idea about, I think broadly speaking, where academics can fit into a lot of these conversations. It's also, I think, a good one to end with. This is, both Dio and Rebecca mentioned the benefits, one of the benefits being greenhouse gas emissions. And what I'm going to do today is really dive deep into that and be very quantitative, I think, in our discussion about where waste energy and landfill sort of lie when it comes to processing waste. So first and foremost here, I have to acknowledge my funding. So the funding for this work was provided by Covanta, but it's incredibly important to say that this is an independent analysis. So when we were signing contracts and doing all that kind of stuff, it was very, very clear that we would present the results that we got, even if they were unfavorable to Covanta. So the three authors listed are the three authors. Covanta was and continues to be a phenomenal industrial partner, and really just an absolute pleasure to work with Covanta and to learn from the colleagues in the local Niagara Falls facility, but also the sustainability folks in the corporate offices. I think this project is a wonderful and absolutely wonderful demonstration about how industry and academics can work together. So I'm an engineer. I'm in UB School of Engineering and Applied Sciences. Specifically, I'm an environmental engineer in the Department of Civil Structural and Environmental Engineering. My colleague Michael is in our interdisciplinary Renew facility, and Mohsen was with me in SCAS. So this isn't, this isn't Philip Morris paying me to tell you that smoking is healthy or anything like that. This is an independent study. So anytime I'm have the opportunity to speak about municipal solid waste and waste energy, whether that's in a classroom or in a conference, slide number one is always this table. This is a table that I absolutely love to hate. Okay, and I'm going to describe why I love it, and then I'm going to describe why I hate it. And so, it provides a lot of information. So one of the things that I always like to point out is we see all these buses that say, natural gas, it's a green bus, it's a green fuel, things like that. And I think a lot of folks don't know where that comes from, but this table does a very good job of describing that, because you can see that, natural gas, while it has a similar amount of carbon as coal, about 75% if you're going to average the different coals, it has about twice the energy value. And so natural gas is not a green fuel. It's not a clean fuel. It is a greener fuel. It is a cleaner fuel than coal. And a table like this can tell you exactly why. I come from Illinois, which Illinois has a lot of coal in it, but it's a high sulfur coal. So you can kind of see where our coal falls into the mix, learn a little bit about oil. So that's everything that I like about this table. Now, what I hate about this table is this line down here, municipal solid waste. Okay, so clearly this table is arranged to make municipal solid waste look bad. That is the point, right? You can see it has a very low energy content. They even get a little special asterisk to highlight the fact that there's a bunch of chlorine in municipal solid waste. But the reason I hate this is because it's irrelevant. Okay, there is no situation where we should ever be comparing municipal solid waste to coal. There is no situation where we should ever be comparing municipal solid waste to natural gas. Okay, it is an apples and oranges comparison, and we are looking for apples to apples. And so to do an apples to apples comparison that involves municipal solid waste, there is only one thing that we can compare it to, and that is landfilling. So anytime I'm doing an analysis that deals with municipal solid waste, you're only going to see one set of comparisons, and that's going to be the landfilling. And the reason is simple, right? We're generating trash. The trash that isn't recycled or composted, there's two options for, right? It can go to a landfill or it can go to WTE. And so those are the only things that should be compared to each other. Right? We should not compare it to other fossil fuels. And I think a lot of people in this room feel the same way. A lot of people know this. A lot of people have used a table like this to disparage, I think, waste energy in the past. And so when I present this to my students or to other audiences with maybe less technical expertise in this realm, I think it's always important to start with this conversation. So the logical solution, right? We know we got a waste problem in this country, and the logical solution is quite easy. We should generate less of it, right? We should waste less. It's always interesting to me, you know, the first people, the people that are loudest about this argument of wasting less are the folks that work in waste energy, are the folks that even work in landfilling, right? These are sustainably minded, you know, climate forward, environmentally thinking professionals, okay? And they are the first to say that we absolutely need to waste less. That is the solution. But are we? Of course we are not, right? So this is total waste generated from 2000 to 2017, even recent data, right? There's basically no change. In the United States, we like our trash and we generate a lot of it. And really there hasn't been any change in terms of where that trash is going, where that waste is going. So recycling, you know, maybe you're taking a quarter of it or so to go to recycling, composting a small amount, maybe it's increasing gradually. You know, we're seeing big New York State, obviously, we have a big composting initiative coming down the pipeline in a couple of years here. And then you have waste energy and landfilling. And as I said, you know, that mix isn't changing. It's a fairly stagnant distribution here. And so it's fine to say we should waste less, but the reality is that we're not wasting less, right? We continue to generate essentially the same amount of waste. And, you know, this doesn't even tell the whole picture because this is on per capita, right? But per capita is not a stagnant number, right? Or the number of population, the population is not a stagnant number. So from 2000 to 2015, you're looking at an increase in population of about 40 million people in the United States. Okay, so even though each individual is generating the same amount of waste, there's more individuals, and so there's more waste. So this is just an enormous problem. Again, I think maybe I'm preaching to the choir a little bit here, but we got to figure it out. We got to deal with it, and we need to have this discussion about waste energy and landfilling. So if you look at those numbers, you take out the recycling, you take out the composting, we see that about 75% of the waste is being sent to landfills. We love our landfills in the United States. Okay, so there's a lot of ways that I can tell you this story, but the reality is that this is inconsistent with a lot of developed, highly developed countries. So I'm going to go to Europe. You know, as I said, there's about 1,000 different tables and graphs that I could show you here to make my point, but we're 75% of that waste going to landfills. The target in Europe was in 2006, so we're talking 15 years ago, was 75%. You have very highly developed countries, Germany, Switzerland, Austria, Denmark, Sweden, that are basically landfill free. Almost none of their waste is ending up in landfills. And so it's safe to say that something different is going on in the United States, right? That for some reason in the US, we like landfills and we don't like waste energy. And I think this is it's a fascinating question. It's a fascinating problem. But I think it really boils down to something very simple. Why is the US not embracing waste energy? Well, we're huge, right? There's really no problem with us putting a landfill at every corner or every municipality anyway. Okay, we have no space constraints. That means that we have the space for the landfills and the landfills can be cheap because we can always just build another one, right? If it fills up, we just build another one. Public opposition. Okay, so, you know, I'm sure the folks in Covanta think about this all the time, this sort of fear of air pollution. It's an outdated opinion. Okay, so this is data comparing 1990 to 2005, which, by the way, is 15 years ago, so things have only improved since this. But if we look at a lot of those contaminants that folks have been scared of, there was a time, you know, if you look at some of these numbers, there was a time when this might have been a justifiable position. there was a lot of emissions that were coming from some of these facilities, and it could have been viewed as very problematic and unsafe and things like that. But that time has passed. Okay, you're looking at mercury numbers down 96%. Dioxins and furans, which actually when I was in grad school, I traveled to Taiwan, and I lived and worked in Taiwan for quite a while, specifically to look at control technologies for dioxins and furans. The reason I went to Taiwan is because they had lots of waste energy facilities, and this was a real problem there. But you're looking at greater than 99% reductions in dioxins and furans. And so this idea of the public just this general opposition, I would say, is an outdated mindset. And finally, costs. The cost issue is significant. It's one that people need to think about. But I think with the right backing, with the right government backing, government support of these ideas and these technological accomplishments, much like the ones Rebecca talked about before me, the capital cost problem can be addressed. And so as an academic researcher, as a person that teaches sustainability to students and is invested both personally and professionally in fixing and speaking about the climate crisis that we're in, I could very easily argue that these things are irrelevant. These are not the questions that we should be asking when it comes to this discussion of landfill versus waste energy, right? Because we have the space doesn't mean that we should use this space. Right? That just doesn't make a lot of sense. And as I said, this opposition problem is kind of irrelevant at this stage. And so what I'm interested in is CO2. Okay, so to me, as somebody that approaches problems with climate and sustainability, first and foremost, I could argue, this is the question, this is the type of question that we need to be asking in a conversation like this one. Is one better from the perspective of equivalent greenhouse gas emissions? Okay, if we shut down all the waste energy and all that waste instead went to landfills, would we have more or less CO2? It's a fairly simple question, a fairly simple way of tackling this challenge. Obviously, the calculations aren't so easy. I'm going to present to you how we did some of those, but that's the way that we think, and that's the way that I approached this problem in this analysis. And so very specifically, we worked with Covanta Niagara Falls, and we said, if tomorrow that facility shut down, and all 800,000 tons per year instead went to representative landfills, would we be greenhouse gas positive or greenhouse gas negative? Would they increase or would they decrease? So ash, as Rebecca talked about, she commented on greenhouse gas emission saving with ash. That was filtered into our model, that factored into the calculations that you're going to see. Dio talked about organics management and how sending some of these organics to a landfill is generating methane, whereas there's, if we can convert those to CO2 instead, that's kind of a zero-sum gain because it came from CO2, went back to CO2, it's biogenic carbon, not too big of a deal. And so, those two topics that were talked about are going to be folded into the mix here in this story as well. So broadly speaking, we considered 3 different categories of emissions, or 3 different places or fields, I suppose, where the emissions might be coming from. So we asked questions about transportation. We said how much waste, where is it coming from, where is it going to, what's the method of transportation. Then we talked about the process. So what's the composition of that waste, what types of landfills, and what are the landfill options that would be attached to those different landfill types. How does the waste energy facility function? You'll see in a second that the WTE facility in Niagara Falls is a massive steam generator. And so that was a very favorable aspect of that facility when it comes to greenhouse gas emissions, because it's displacing natural gas, essentially. And then collection efficiencies and landfills do generate methane, and some of that methane is captured. And so we need to consider that. We need to think about how much over the lifetime of a landfill, how much of that methane is captured, how much electricity can be generated from it, what is displaced by that electricity, who are the waste energy customers, where would the electricity otherwise be coming from? So all of these questions, you're not going to see answers to everyone, but they're all bundled into the analysis and the responses that I'm going to show you in a couple slides here. So our collaboration with Covanta, it's important to say this here, it provides novelty. So people can model things. People have modeled this question. But what we uniquely had access to was data. Okay, so Covanta was very much an open book with us, willing to provide essentially anything we asked, you know, in terms of the data that we needed to answer the questions that I presented to you in the previous slide. So for the most part, our analysis for Covanta was not a model. It was based on actual numbers. We used some emission factors and talked about global warming potentials and things like that, but most of the numbers were real. It wasn't just input waste, output CO2, right? We knew the amount of steam, we knew the amount of electricity, we knew supplemental gas consumption, all of that. So we had all the information on the waste, where it was coming from, how it was being transported, industrial, municipal waste streams. It's a fairly large facility, pushing 1 million tons per year of waste. We had full composition data, fossil to biocarbon. That ratio I'm going to discuss quite a bit moving forward. That was one of the independent variables we looked at quite a bit. We had their steam output data, electricity output. You know, they have customers that demand their steam and that demand their electricity. So if for some reason a facility is down, they do need to consume some supplemental natural gas to make sure those customers are happy. So that was obviously a negative when it came to greenhouse gases that we weren't willing to ignore, of course. And so that was part of our calculations as well. So again, I really can't stress how great this partnership has been. Very professional, very collaborative, I would say. And then our estimates for the landfills came from the Municipal Solid Waste Decision Support Tool, which is an EPA model. Now, a comment on models: anytime I present at conferences about this work, somebody wants to argue about models, and that's fine, right? Models have pros and cons. That's par for the course. There's no, I'm not going to sit here and say that this model is perfect and it considers absolutely everything and every assumption is conservative and everything like that. It's just not the case. But whatever model they're going to throw at me, I'm going to make the same arguments back at them. Okay, so the reason we went with this model is because in the literature, it's arguably the most common. It's government supported, right? It's an EPA model, and so it doesn't have a bias attached to it. And you know, we thought that for the analysis we were presenting, it was the best choice. So all of the landfill data that you're going to see is based on this model. A little bit of the process emissions for the Covanta facility are based on this model as well, so that the overwhelming majority of our Covanta data was real data, but a little small kind of fraction, including some of the ash stuff that Rebecca talked about, was modeled. And we had to make some assumptions. Okay, these are you know, literature kind of standard, not anything too controversial here, I would say. We assumed that the landfill gas would be converted to electricity with an ICE. That's 33% efficient. Displaced CO2, so any electricity that's being generated would have otherwise come from a combined cycle natural gas plant. The idea there was that this would be sort of comparable to like a peaking unit, which would be gas-based, kind of easy to turn on and off. And then displaced CO2 from steam would have come from a natural gas-fired steam generator with 75% efficiency. So our transportation calculations were interesting. For Covanta, for the waste energy facility, it was easy. We had everything. We had masses, we had locations, we had transportation types. Life is good, right? We just, you know, we knew where it was coming from, we knew what it weighed, and we knew the method of transportation. So if it came, you know, X tens or hundreds of miles by train, we put in the weight, we found the emission factor, and we got our greenhouse gas emissions. If it came, you know, 200 miles by 16-ton truck or something like that, we got an emission factor and we put it in. So very, very confident in those numbers. Really no modeling involved whatsoever. A little trickier for landfills, right? Because we're saying if the waste is not going to Covanta, where's it going to go? And so the way that we addressed that problem was to say, for all these waste sources, which we knew, we figured out where the 5 closest landfills were, and we averaged that distance and said it would go there by truck. So, you know, I think it's hard to say that those assumptions were controversial or anything. I think it was a pretty fair way to treat the transportation piece. And so these are the variables we looked at. We have a lifetime landfill gas collection efficiency. So as I said, all of the methane that's being generated at a landfill is obviously not emitted to the atmosphere. We would have a huge problem if it was. 60% is a value that seems to me in the literature to be pretty well accepted as a 100-year lifetime for a landfill. About 60% of the generated methane is captured. We wanted to have one that was above and below that, and kind of just for our fun, we also wanted to have one that was a 0. Methane's global warming potential. So the textbook value for this is 25. Oh, sorry about that. The textbook value for this is 25, but that value is increasing, and I'll talk a little bit about why. So we went with 25 and 34, which is increasingly becoming the accepted value or closer to the accepted value for methane. The global warming potential for biogenic carbon, as I mentioned earlier, the applicors and the yard waste and all that kind of stuff came from CO2, and now it's going back to CO2. So typically biogenic carbon is thought of as having a global warming potential of 0. However, again, in the recent literature, there's some discussion about that because of kinetics. We burn it instantaneously, but the plants take a season to grow or a year to grow or whatever it might be. So some folks are using kind of an upper end of 0.32. So we wanted to use a landfill friendly, if you will, assumption and see what that number would do to our analysis. Fossil CO2 is 1, can't really change that. That's a definition. And then we had the bio to fossil fraction. So for the year of data we looked at, 0.56 was the actual value, and we picked something above and something below to see how that played with our numbers. All right, so the results. I got about 5 minutes here, which is perfect. So first things first, we have, the first thing I want you to look at here is the little tiny blue bar, okay, on each of these. So this is the variable we're changing is landfill collection efficiency. These first 4 are the 4 values we looked at, and it's comparing it to the existing WTE situation. So this little tiny blue bar here is transportation. If you could zoom in, you would see that the waste energy bar is higher. That makes sense, right? As I said, we have a landfill on every corner. Okay, so we're not transporting very far if we're going to a landfill. But what this should tell you is that it kind of doesn't matter, right? In the grand scheme of things, that transportation piece is pretty insignificant. And so instead, we're going to focus from here on out on displacement process, and really I'm going to focus on the total emissions. And so you can see the 60%, as I said, is kind of the understood value for lifetime collection efficiency at a landfill, and WT is lower. Okay, even if we do a very landfill friendly, say we're going to collect 75% of that methane over the lifetime, you're still at displacement being over 300% better, and overall emissions being quite a bit lower as well. Obviously, the landfill that collects no methane is huge for total annual emissions. But even these more realistic scenarios, and for that matter, the unrealistic 75% scenario, still are exceeding the total emissions from waste energy. We looked at global warming potential without going too deep into an atmospheric sciences discussion. Basically, every gram of CO2 that we emit decreases the impact of CO2. And if we're decreasing the impact of CO2, that means that the relative impact of all the other greenhouse gases increases. Okay, so this is why we used to say methane was 25 for a global warming potential. Now we're close to 34. So from a landfill perspective, that's obviously going to increase the greenhouse gas emissions. Doesn't really affect WTE, because WTE isn't really, methane's kind of irrelevant, right? Other than some of the supplemental natural gas consumption, it's really not a factor. Additionally, we looked at, if we say that biogenic carbon is 0, and we compare that to if we say biogenic carbon is 0.32, that's going to hurt waste energy because they're generating a lot of biogenic carbon. And you can see this bar was about here, and now it's all the way up to there. But it's still, even if we give that landfill friendly assumption, it's still much lower emissions than the landfill scenario. Okay, so we're trying to be conservative in the way that we approach this problem. And then finally, the bio to fossil ratio. As I noted, if we burn a lot of biogenic carbon, that's obviously friendly for the waste energy situation, because those emissions are less than 1 from a global warming potential perspective. And so you can see that in this case where we have the most biogenic carbon, we see the lowest overall emissions. In fact, it's actually a negative number, which means it's an improvement compared to just burning or generating electricity from natural gas, which again, I said I would never make that comparison. But you know, in this case, I'm going to make an exception because it looks really good. And even in this scenario over here, you know, maybe with the plastics crisis that we have right now, maybe a lot of that gets funneled to waste energy. Who knows where you would get a number like this 0.45. But even if we do drop to about a fossil ratio like that, you still see lower emissions for the waste to energy facility compared to the representative landfill situation. So this is a summary of all those results. Basically, I'm just comparing, you know, I call it a sensitivity analysis, but I'm just comparing the waste energy value to the respective landfill value. And the truth is that we could not create a situation where there was more greenhouse gas emissions from waste energy. Okay? In every scenario, even the unrealistic ones that we came up with, total emissions of greenhouse gas CO2 equivalents was going to be lower for the waste energy scenario. So that's kind of the main takeaway. Even this situation here where we have the 75% landfill gas collection, we're still at notably lower overall greenhouse gas emissions for the waste energy situation. So the last thing I'd like to say is you know, just this idea of moving from reactive to proactive. I think this is the approach that we're taking at UB in our waste management research teams. You know, this idea that engineering exists to fix problems, I don't like, you know, and I think in the waste management sector, we've seen this be a problem, right? China says no more plastic, and all of a sudden everybody's running around trying to figure out what the hell to do. Okay, that's because it was sort of a reactive model there. And we would rather use engineering to prevent problems instead of to remedy or fix problems. And so we have this idea of not working reactively, but instead working proactively. And I think this work here, this sort of modeling analysis, this mixed real data with modeling analysis is a good example of how we're doing that. So with that, I'll wrap up. I think I was less than 25 minutes. I hope I was, Ken.
Yeah, just right on time, actually.
All right, perfect. If there's any questions or comments, I'd be thrilled to take them. Thank you.
Now, there were no questions this time, but I will reiterate, because I remember when Covanta was talking about doing this study with the university, and you know that was it. That was the exact kind of discussion. Like, well, we don't know what they're going to come up with. We hadn't dealt with you guys before. We hadn't given, you know, any primers, and just, you know, helped you, gave you the data, but you know, we were confident enough in that, you know, that this idea of the greenhouse gas benefits of waste to energy it's not new. Certainly, it was started in Europe, the IPCC, and a lot of the EU focus on greenhouse gases has looked at this, and it's just, you know, like John said, there are other factors here in the U.S. which makes it not quite as take off quite as quickly. With that, you know, certainly no other questions come in for any of the presenters. I would like to thank John, Dio, and Rebecca for their time. Certainly all very interesting presentations, and not an easy task presenting without any audience feedback. So just moderating, I found it challenging. I can't imagine doing the 25 minutes. With that, I'll turn it back over to Rich Bills, and hope to see a lot of you back in May in Sagamore.
Hey, thanks, Ken. And thanks to all of our speakers today and throughout the entire conference that we've had. You know, this wraps up the the schedule for the conference, the first virtual conference, I think, that we've done. And, you know, thank you to the Federation for putting this all together. Luann Meyer did a great job kind of spearheading it. People on the subcommittee who were part of this. I will mention Luann Meyer, Kelly Timbrook, Bruce Howie, Russ Rutkowski, sorry, Savannah Petrowski, and Lisa Vergaro, all who were on this committee to kind of put this thing together. We've been dealing with the COVID disruptions to our life, and it's nice to be able to still do the things and have conversations and listen to people talk about the things that we're all interested in. I also like to thank Bart and LaJudas for helping with all the mechanical stuff here and with Luann's time. I'd like to turn it over to Luann to do a little finishing chat with everybody, if that's okay. But I want to thank everybody for participating today and throughout the conference. And Luann, you ready to go?
Yep, I'm ready.
All right, thank you.
All right, thank you, Rich. So I just want to take a moment to thank everybody who attended over these last 3 weeks. We've come a long way and we've learned a lot. You know, just thinking back to the 3 weeks of virtual sessions that we've had, you know, we've covered COVID-19, PFAS, recycling markets, landfill covers and odors, odor mitigation measures, our lively discussion of EPR this morning, and then finishing up with trash today and power tomorrow. And, you know, everybody did a great job. I put up here, I just want to thank the moderators for keeping everybody in line. And Kelly and Rich were the facilitators, and I did that one day. It all worked quite well. And I want to thank all the speakers. We had 24 speakers over the course of these 3 or 6 sessions. And without them, obviously, we wouldn't have a program. So I think we covered a lot of challenges that we come across, but also a lot of opportunities that we see in our industry moving forward. So with the last, and then I just want to say thank you to Dan Sheridan at BNL. He was the man behind the scenes and made sure that everything worked at least the best we could possibly make it work. And then don't forget to submit your abstracts for next year's conference, as well as consider attending the NISAR conference that's coming up, the virtual conference, as well as SWANA's MERC Summit. So with that, I'll say goodbye, and we hope to see you all again soon, virtually, or hopefully sooner in person. Take care.